Welcome to Brain Vision.
Our question says it wants us to view figure 45 as reference for this question. And it says a current I flows in the circuit clockwise as shown. And for part A, it wants us to determine the magnitude and the direction of the magnetic field at the center, C. Okay, so to find the magnetic field and the direction at the center, C, we're going to break this into two different loops. The loop which has the radius R1 is the top semicircle, and the loop which has the radius R2 is the bottom large semicircle. So for part A, the magnetic field at a point C can be obtained by using the Biot-Savart law, which says which is useful for determining the magnetic field due to a known arrangement of currents. So what does this law say? Well, I'll go ahead and write it out here. It says that the change in magnetic field, dB, is equal to mu naught, just the magnetic permeability of free space, times the current that's producing the field, I, divided by 4 pi. And then this is multiplied by the cross product of dl. Let's make that look more like an L. There we go. Cross the unit vector r, divided by the radius that we're considering r squared. So again, here dB is the contribution from the magnetic field. I is the current passing through the small length, d sub L. So dl is the small length that we're considering, this infinitesimal length change. And r hat is the unit vector along the path. The magnitude and the direction of the magnetic field at point C along the path of the straight wire will be 0. So the magnetic field is only due to the semicircular portions. So we can break these into the top semicircle, which we'll call 1, and the bottom semicircle, which we'll call 2, since the top one has radius R1 and the bottom has radius R2. So from the top one, what we have, maybe we should indicate this as part A first. We have B1 is equal to the integral of dB1. So we can replace above for dB1. We can replace what we have written above. So I'm going to go ahead and pull out some things that are constants, right, outside of the integral. So we have mu naught times I over 4 pi times r squared, but the r in this case is r1 because we're considering the top semicircle. So this is times r1 squared. And then so in the integral, we have dl cross r hat. Okay. But we can further simplify this even more, because dl cross r hat, remember that that r hat is the unit vector along the path, whereas L is the small infinitesimal length. So if you do L cross R using the right-hand rule, you get what we're going to call k hat, which is going into the page, right? So we'll say that L cross R gives you k hat, or negative k hat, and we're going to find the negative k hat direction that's going into the page. So this gives you mu naught times I divided by 4 pi r1 squared times negative k hat, and then we're still integrating over the infinitesimal length dl. Okay, so carrying this out even further, the integral over the infinitesimal length dl gives us pi r1, because it's half of the circumference. So it's not 2 pi r1, it's just pi r1, because we're considering half the circumference here. It's not a full circle. So what that leaves us with is mu naught times I divided by 4. The pi's cancel, right? Because there's a pi on bottom, and then the dl integral gives us a pi. So those cancel. And then one of the r1s cancel, because we have an r1 squared on bottom, and we're going to end up with a r1 from the integral of dl. So we end up with mu naught I over 4 r1. And then this is in the negative k hat direction, or you could also say into the page, either one. Okay, now we need to do the same thing for the bottom semicircle, B2. So B2 is going to be equal to the same type of integral. It's going to be d B2. And it's the same expression, except now we're replacing R1 with R2. So if you go back here and look what we have, it's, again, the exact same expression, but we're going to replace R1 with R2. So our results of the integral are going to be the exact same, except we're replacing R1 with R2. So let's just, without having to carry out all of the operations, it's just going to be the exact same as before, except replacing R1 with R2. So the result is going to be mu naught times I divided by 4 times R2 acting in the negative k hat direction, or you could also just write into the page. Either one should work. Okay, so then our total magnetic field, B, is going to be a linear combination of the two magnetic fields from each semicircle. So this is going to be B1 plus B2. Oh, B sub 1 plus B sub 2. Okay. So now that we know that they add together like this, oh, and by the way, if you wanted to figure out, if you're struggling to understand where the negative k hat comes from, where the into the page idea comes from for these B values, go ahead and take your right hand and curl your fingers in the direction of the current that's running over the top semicircle and see which direction your thumb points. It's going to be into the page, right? And then the same thing with the bottom loop. Curl your fingers in the direction that the current is going and see which direction your thumb points. It's also going to be into the page. So you could also use the right-hand rule to get that justification. So that is the reason that B1 plus B2 is going to increase, because they're both contributing to a magnetic field that's acting into the page. So what we end up with here is mu naught times I over 4, because those are constant and all. So I'm just going to pull that out front. So mu naught I over 4. And then you have 1 over R1 plus 1 over R2. And these are all acting in the negative k hat direction. You could also, if you wanted to type out into the page, just to be specific, you could. So we could go ahead and box this in as our solution for part A. Part B says it would like us to find the magnetic dipole moment of the circuit. So the magnetic moment is the product of area and current. The area is the sum of the half circles, and by the right-hand rule, the direction of the current is going to be going into the page, right? Or at least the magnetic moment is going to be going into the page because of the direction of the current from the right-hand rule, as we had previously described. So for part B, then, we'll indicate that as such. We have magnetic moment, mu, and it's a vector, so we'll indicate it, is equal to the current, I, as I said, times the area, and then the direction from the right-hand rule that this is acting is into the page, k hat. Okay, well, the area is the area of the top semicircle plus the area of the bottom semicircle. So we can call this A1 plus A2. And then again, negative k hat. Okay, well, what is the area of the top and the bottom semicircle? They're simply equal to 1/2 pi r squared, where r is the radius of the two semicircles. So we can replace those, and we have pi times r1 squared over 2. So it's 1/2 pi r1 squared plus pi times r2 squared over 2. And these are still going in the negative k hat direction. Okay, and then just to simplify this a little bit more, we can pull the pi out front as well as the 2 out front. So we end up with I. We can pull the pi out front, the 2 out front, and we can also pull the negative out front from the k. So we'll really make this a lot more simple to read. So we have negative 1/2, the 1/2 from the 1/2 pi r squareds, times pi times I. And then this is multiplied by r1 squared plus r2 squared. And then this is in k hat. So I pulled the negative from the k hat out front, so we can box this in as our solution to part B.